As we move from left to right in a periodic table, the atomic radii of an element is going to decrease. Why atomic radii will follow this trend? Because in moving from left to right in the periodic table, what we have observed that we can see that if the effective nuclear charge is going to increase, it will attract the electron towards it. So if the electrons attract towards the effective nuclear charge, the size of the atom will automatically going to be reduced. So this trend is followed in case if we are moving from left to right in the periodic table. So left to right means if we are moving along period. So what will happen here if we are going to move along the period? If we are moving along the period, the atomic size gradually decreases. Why atomic size is gradually decreasing? Because number of shells that are added to the atom has been low. It means no number of shells has been added, and the increase in the effective nuclear charge will trying to attract the electron towards itself, and the size of the atom will going to be automatically reduced. So from left to right, it means along the period, atomic radius is going to be decreased. Atomic radius decreased. So why in moving from left to right atomic radius is decreasing? Atomic radius is decreasing because no new energy shells are added. Firstly, this is the reason no new energy shells are added. Secondly, if no new energy shells are added, the increase in the effective nuclear charge. Increase in effective nuclear charge has a large effect on outermost electrons. If it has a large effect on the outermost electron, it will exert a force on the electrons, and this force of attraction lead to the contraction in the size of the atom. So what will happen next? This will lead to the force of attraction leads to decrease in size, and due to this decrease in size, the atom contracts. So this is the trend that we go from left to right, we are following in the periodic table. Now what will happen if we are going from top to bottom in the periodic table? So let's see what will happen if we are moving from top to bottom. So after left to right, we are considering top to bottom. Top to bottom means a long group. Now, what will happen in this case? As we are moving from top to bottom in the periodic table, new energy shells has been added. So, if new energy shells has been added, the nucleus has less effect on the outermost electron because it is far from the nucleus. Now what will happen if the nucleus lose its contact with the outermost electron? The size of the atom will automatically going to increase. It means from going from top to bottom, what will be the trend in case of the atomic radii? The atomic radii is going to be increased. So we can see that in going from top to bottom, atomic radii increases. Why atomic radii is increasing? Because new shells are added. Because new shells are added, if new shells are added, the nucleus has a less effect on the outermost electron. So we can say that nucleus has less effect on outermost electron. So if it has less effect on the outermost electron, the size of the electron cloud will go on automatically increasing. So what will happen next? The size of electron cloud will increase because there is no effect of the nuclear charge on the outermost electron. So we can say that atomic radii increases. So hence, atomic radius increases in going from top to bottom. So the trend we are discussing here is very important because most of the questions that arises in your competitive exam has usually asked from this topic, that what will be the trend in atomic radii, ionic radii, and the next term we will going to discuss that about the ionization enthalpies, electron gain enthalpy, electronegativity. So they are going to ask you about how these metals or non-metals or the compounds in the periodic table will going to form this type of the trend. So in the trend, that what will going to be increased, what is going to be decreased, such type of questions that is of the increasing order and the decreasing order are much important. This is the trend in the atomic radii we have discussed here. I am repeating it once again, that in case of the atomic radii, what we have seen that in moving from left to right, atomic radii decreases. In moving from left to right, atomic radii is going to be decreased because no new shells are added and the nuclear charge has a much force of attraction on that electron. So it will try to attract it and usually the size contracts. But if we are moving from top to bottom, we are moving from top to bottom, the atomic radii is increasing. Why this atomic radii is going to be increased? The atomic radii is going to increase because the new shells are added and the nucleus has its less effect on the outermost electron, so it will able to expand its electron cloud and consequently the atomic radius is going to be increased. So this is how the atomic radius will going to show the trend in the periodic table. Now let us move to our next terms and we will see how they are going to form the trend in the periodic table. So let's move to our next term. So you can see that these are the simple classification of the atomic volumes in the moving from left to right in a group. So what you are observing here, in the trend for moving from left to right in the periodic table, we can observe that the atomic volume is somewhere that is decreased for some of the elements. This is a decremental value for some of the elements, and then after there will be a slight variation that again it will going to increase in the periodic table, and again it is showing in the trend that they are automatically increasing in the periodic table. So what the trend we are observing in case of the atomic volumes in going from left to right in the periodic table is going to increase. Why it is increasing? Because of the addition of the new energy shells. So what points we have to consider here? From left to right in the periodic table, atomic volume is going to be increased. But what trend it is following? It is lowest in the first part, then in the middle part it is going to decrease or somewhat increase, and then it is again showing the trend of the increasing atomic volumes. So we can say that it is following the gradual trend. It means there is not a increasing or the decreasing part. It have some uncertain increment or decrement. So we can say that it is because of the addition of the new energy levels. This is happening because new energy levels are added. New energy levels are added. Now, what will happen in the group? You can see here, in going down the group, the atomic number is increases. So, we can say that from top to bottom, atomic volume will increase. But in this case, firstly, it is increasing in the first part. That in the middle part, it is somewhat decreasing, and then in the last part, it is again going to increase. Now, from top to bottom, you can easily observe that if I am going from top to bottom, you can easily observe that atomic volumes are going to follow the trend of the increasing demand. So, it is increasing because as the number of valence electrons are added more in the valence shell, you can see that the size of the atom is going to increase. As the size will increase, the atomic volume will gradually increase. And there is the effective nuclear charge, it is also going to be increased in the periodic table. So, what we have observed in the left part of the table, in the left part, the first reason is observed. And in the last part of the table, the second fundamental will going to be increase. So, what are the two reasons for this? The two reasons are effective nuclear charge increases. Effective nuclear charge increases, and second, number of valence electron increases. Number of valence electron increases. So, if effective electric charge, nuclear charge is increased and the number of valence electron are increases, we can say that atomic volume will gradually increase because on adding more number of the valence electron, the size of the atom or the size of the element will going to be expand. And we know that atomic volume is generally expressed in centimeter cube. This is the basic unit for representing the atomic volumes. Now, you can see that the first reason, that is effective nuclear charge. This first effective nuclear charge is going to be increased in the first part. This will be for the first part. And the number of valence electron is going to be increased in the last part of the periodic table. So, in the first part, you can see that effective nuclear charge is going to be increased, and in the last part, you can observe that number of valence electron is going to be increased. So, this is the trend of atomic volumes in the periodic table, and what it has been observed that francium will have the highest atomic volume, that is at 87 centimeter cube. So, one more conclusion we can draw from here. This is a note. Which element having a highest atomic volume? Francium has highest atomic volume. And what is the atomic volume for that francium? It is 87 centimeter cube. So, this is the trend in case of the atomic volumes we have observed here. So, copy it from here so we can proceed to the next one. Let us move to discuss about the trends in the density. So, the fourth category of classification will be density, and the basic unit for calculating the density here will be gram per cc. And density is what? Density is basically a mass upon volume. The mass per unit volume is known as density. Now, what you have observed in case of the densities in the periodic table, as we know that atomic number will increase, the density of a substance will going to be increased. So, we can see that in the periodic table, that if we are moving from left to right, we can see that firstly the density will be increasing for some of the elements, then it will become constant somewhere 2.26 and 2.234, and then again it will start going to be decrease. It is again going to decrease in the left to right in the table. So firstly, density is related to the increasing in the atomic number. It is first showing the increasing trend, then after it become constant, and again it is showing the downward slope. It means it will again decrease in the group. So we can say that density of a substance will vary with atomic number. So if the density is going to vary with the atomic number, so what will happen? Firstly, for some elements it is increasing. Firstly, for some elements in the starting, it is increasing. Secondly, in the middle part, it is constant somewhere. So in the middle part, it is constant somewhere. Then you can observe that in the last part of the periodic table, it is again going to be decreased. So in the last part, it is going to decrease again. So this is the trend in the case of a density of a substance that is observed in the periodic table. Now you can see that for the liquid state, that is the mercury will having a density of 13.6 gram per cc, which is actually the very much greater density in case of the liquids. So we have one more note here. So the note is, in case of liquids, mercury has greater density. And what is the value of the density here? The density is actually 13.6 gram per cc, which is very high in case of the liquids. So this will be the density for the mercury here. So again I am repeating, you can see the trend in the case of the densities. The density is first increasing as we are moving from left to right. You can observe here. Then it will become constant somewhere. It is become constant somewhere in the periodic table, that is in moving from left to right. And again it will gradually show a decrement in the properties, that is that, see here 4.519, 5.77 and 3.19. It has been reducing again. So this is the trend in case of the densities here. Now after density, we have another topic that is about melting and boiling point trend. The melting and boiling point of a substance is going to be increased with the increasing atomic number, but those which have low atomic volumes will have a high melting point, and high atomic volumes will have a low melting point. But melting and boiling point are usually calculated in the degree Celsius, and it is maximum for tungsten if we are comparing metals, and it is maximum for carbon if we are comparing known metals. So let us have a look at the melting and boiling points. So now the next topic is about melting and boiling points. So this is a curve for the melting points we have observed in some cases. So according to this curve, what we will observe that, according to this periodic trend, we can observe that melting point increases with increasing atomic number. it is going to increase with the increasing atomic number. It is usually represented in degrees Celsius. Melting point is represented in degrees Celsius. Now what we have observed in this table, the melting point is increasing. Firstly it is increasing, then after it will become constant here. It is constant here, then again it will show the gradual decrease in the changes. See here, it is again decreasing. So what we have observed, the trend in the case of the melting boiling point, in first part, melting point is going to increase. In first part, melting point is going to be increased. In second part, that is middle of the table, it become constant somewhere. It is constant somewhere. And in the third part, that is the last one. In the third part, it will again going to be decreased. Melting point is again going to be decreased. So this is the trend in case of the melting point we have observed here. Now, what more conclusion we can derive according to this melting point? If atomic volume is greater, if atomic volume of a substance is large, the melting point will be low. The melting point will be low and vice versa. It means if atomic volume is low, the melting point will be high. So the melting point will be high. So this is in trend with the atomic volume of melting boiling points. Now, in case of the solids, tungsten will having a large melting point, but in case of the liquid, carbon is having a highest melting point. And if we are comparing about the lowest melting point, the lowest melting point will exhibited by the helium only. So, in case of solids, we are taking solids, metal, and in case of metals, in case of non-metals or lowest melting point, and this will going to tell us about the highest melting point. So these are the trends in the melting point we are observing here. So in case of the metals, which metal will having a highest melting point? The tungsten will going to show the highest melting point. If I am comparing non-metals, in case of the non-metals, carbon will have a highest melting point. And what about the lowest melting point? The lowest melting point will be shown by helium. So the helium is going to show the lowest melting point. So this is the observation in case of the melting point we have seen here, but the boiling point is not going to show the similar trend. It will follow some sort of similar trend, but it is not as sharp as a melting point we have observed here. So this is about the melting points here. Now let us consider some of the radiuses here. So we will start with our new topic, that is about the atomic radius. That how atomic radius will going to show a trend in the periodic table. Now let us start the topic, that is about atomic radius. Now, what atomic radius is? Atomic radius is actually the distance between the nucleus and the last electron that is present in the outermost shell of an atom. Suppose if I am drawing a structure of atom like this. So, what is this composed of? This composed of the positively charged nucleus here. This is our nucleus. And suppose the electron is moving in this shell. This is our electron. This is electron. So, this part is nucleus and this part is electron. So, what is atomic radius? In an atom, atomic radius is actually the distance between the nucleus and the electron. So, the distance between the nucleus and the electron is known as atomic radius. So, this is actually the atomic radius. Now, atomic radius is not an individual term. It is actually divided into 4 parts. So, we can say that atomic radius is actually having a 4 parts. So, what are these 4 parts? These are covalent radius. Second one is van der Waals radius. Third part we have is about metallic radius. And what is the fourth part? The fourth part we have is about ionic radius. So, these are the 4 radius we are going to discuss now, and we are seeing for a trend that the periodic table, in the periodic table, how these radiuses will follow a trend. So, let us deal with all these type of radius one by one. So, I hope what actually the atomic radius is, it has been cleared to you. Now, let us move to our first type of the radius, that is covalent radius. Now, what actually the covalent radius is? It is half of the internuclear distance between 2 covalently bonded atoms. So, what is covalent radius? Let us start here. First topic is about covalent radius. Now, what is covalent radius? Covalent radius is defined as a, half of the internuclear distance between 2 covalently bonded atoms. 2 covalently bonded atoms. It means when 2 atoms are bonded by the covalent bond, we can say that a covalent radius will exist between them. So, how the covalent radius can be identified? Suppose we have the 2 atoms here, and this will be formed by the overlapping of the atoms. Suppose this is my atom number A and this is my atom number B. Now, what is the internuclear distance between these atoms? This is the nucleus of atom A and this is the nucleus of atom B. So, this is our internuclear distance. So, what is internuclear distance? The internuclear distance is here is AB. Now, what we have to do, taken, the covalent radius is half of the internuclear distance between them. So, I can write here RAB. What is this RAB? RAB is covalent radius. RAB is covalent radius, and this RAB will be equal to half of the AB. AB will be internuclear distance. AB will be internuclear distance, and this covalent radius will be equal to half of the internuclear distance. So, we can say that RAB will be equal to half AB. So, this will be the formula for covalent radius. So it is very simpler to learn that when two atoms are covalently bonded, it means they are formed by the overlapping, the half of the internuclear distance between them will give you the covalent radius. Now you can see that the covalent bond is actually formed between the non-metals. So the trend of the covalent radius will be shown by non-metals. This trend will be shown by non-metals. So let us have a look at the covalent radius of some of the elements here. This is the covalent radius for few of the elements we have mentioned here. So you can see that this is the trend in the covalent radius as it is subsequently increases up to sodium, and then after it is showing the decreased graph. Now let us take an example. Suppose the internuclear distance between hydrogen atom is 74 picometer. So we have an example here. Example we are writing here. We have internuclear distance of hydrogen. If internuclear distance in case of hydrogen is 74 picometer, it is 74 picometer in case of the hydrogen, then we can say that the covalent radius will be given by 74 by 2, that is half of the internuclear distance, and it came out to be 37 picometer. So this is all about the covalent radius we have discussed here. Further topics or the further radius we will discuss in our next lecture. Thank you so much and have a nice day.